guys, I'm just going to pick up the example that we were doing in class just to hit, carry on with the idea of average rate of change and average speed versus instantaneous rate of change, or in this case, instantaneous speed. I've got the equation that we talked about in class. I changed the notation slightly. I'll tell you that the distance that an object travels is f at t equals 5t squared, where t is in seconds, and f at t is the distance traveled in meters for however many seconds, right? The first thing I want you to do is draw a graph. So when t equals 0, if I plug a 0 into the equation, I would get 0. Plug a 1 in, I'd get 5. If I plug a 2 in, I would get 20. Plug a 3 in, I'd get 45. And if I plug a 4 in, I would get 80, right? So this graph would loosely look something like this, all right? So 1, 2, 3, 4. So 0, 0. We do this in red. 1, 5, something like this. 2, 20 would look something like this. 3, 45 would look something like this. And 4, 80 would look something like this, right? Now we know that this is quadratic from the equation, so it better be a parabola that goes up like this. Okay, everybody see this? Now again, I don't need the left side because again, this is talking about time as my independent variable and my distance as my dependent variable. Okay, so this is the graph of the distance that this particle travels over time, right? Now if I want to find the average rate of change, what I'm trying to find is basically how fast this particle is traveling over a period of time. So in the first part, or the second question here, it says find the average rate of change for t equals 0 to t equals 4. So starting at t equals 0 until t equals 4, what would my average rate of change be? Well, again, I know at t equals 0, the distance was 0, so 0, 0 would be the point there, and at 4 seconds would be 80, correct? So I know that in number 2, the average rate of change, or my speed, would equal 80 minus 0 over 4 minus 0, which would be 80 over 4, so 20. And in this case, my units would be meters per second, okay? Now, if I did the same thing for the third part, let's find the average rate of change for t equals 2 and t equals 4, then again, I'm going to use 2, 20, and 4, 80. So now my average rate of change would be 80 minus 20 over 4 minus 2. So that would be 60 over 2, so 30 meters per second, right? Now, if you notice, the average rate of change from 0 to 4 seconds is smaller or slower than the average rate of change from 2 to 4 seconds. So if we look at the graph, that says, well, let's see, if I'm finding the average rate of change between 0 and 4 seconds, that would be the line that would have a slope of that 20 meters per second, right? All right, so I know that the slope of this line represents the average rate of change from 0 to 4 seconds. And that would be 20 meters per second. If I drew a line connecting 2 seconds to 4 seconds, right, this guy's slope, or his average rate of change, would be 30 meters per second. Can everybody see that as the difference between these values, say from from 0 to 2, as I get closer and closer, or as I say, as the difference between my x values gets closer and closer to 0, can everybody see that the slope is getting steeper and steeper, right? Can everybody see that? As I travel along this way, it looks like my slope is getting steeper and steeper, right? Okay. So, in part 4, it says, what appears to be happening to the average rate of change is the difference between the two times gets closer and closer to 0. In other words, from 4 seconds to 2 seconds to, say, 1 second, so on. It looks like the average rate of change is increasing. Okay? All right? Well, does it make sense that starting at the beginning, the distance that this guy travels is not very far, but as time continues, doesn't it look like he's going further and further and further, faster and faster and faster? Well, what that must mean is his average speed or average rate of change is increasing. Right? Well, what if I were to find the instantaneous rate of change exactly at t equals 4? All right? Well, that would be the speed that this particle is traveling at exactly 4 seconds, the thing is that I can't actually find his speed because I need 2 points to use, like it's in the slope formula, y2 minus y1 over x2 minus x1. But I can't do that because I don't have 2 points, right? Because instantaneous means it means exactly 1 point. Well, here's where we're going to get a little theoretical, right? We've got to open our mind up. Let's imagine that I do want to create the average rate of change between 2 points, right? But instead of being really far apart in time, like from say 2 seconds to 4 seconds, what happens if I want the average rate of change to be some small little line where the difference in time is really, really small? Would you agree that I would still have 2 points, this point and this point, correct? Right? Well, I could find the slope of this tiny little line connecting these 2 arbitrary points using the slope formula, where I would say, let's see, if this point right here is, I'm going to call this right here, let's see here, I'm going to call this guy x, right? And this point right here is right here. I'm going to call the difference between this x and this x, I'm going to call this distance right here h, right? This point right here will be called f of x, and this point right here will be called f of x plus h, correct? Right? Well, here's what we could say. Would you agree that the slope of this line in general would be f of x plus h minus f of x over, let's see here. Well, this point was x, and this point, if this is h, wouldn't this point right here be x plus h, all right? So this would be x plus h minus h. I'm sorry, minus x, all right? Or in other words, these x's cancel. Wouldn't my average rate of change in general be simply f of x plus h minus f of x over just h, all right? And so in general, if I describe the average rate of change in this way, right, that's how we could do the same problem. But now this h value, where h is the difference between my 2 x's, if you notice that's the same thing as delta x or delta t in this case, right? That number can change. I can pick whatever I want. I could choose 1s or 2s or 3s, but I could also choose really, really small values, right? So if I wanted to find the average rate of change of this, I could use this formula, but what would happen if I applied this limit? What's the limit of this average rate of change as h approaches 0? Well, wait a minute. If that's the case, as h approaches 0, if the gap between these 2 points, between here and here, if that's 0, wouldn't this point here actually turn into, wouldn't this green point, wouldn't this green point right here turn into this green point? Wouldn't it be 1 point? And so instead of being the average rate of change between 2 points, wouldn't it be the rate of change of just 1 point if h is assumed to be 0, right? So I can actually go from an average rate of change to an instantaneous rate of change using this limit idea. As long as h is approaching 0, right? Okay, that makes sense? Right? And so how would the average rate of change compare to the instantaneous rate of change if the difference in time is really close to 0? They would be pretty much the same value, right? If this difference in my x values, or time values in this case, is approaching 0. Now let's take a look at how we can use this to solve a problem. Okay, so here's what we're talking about. To find the instantaneous, suppose I have to find the instantaneous rate of change at 4 seconds. Well, to do this, I'm going to use this idea of the limit. I'm going to take the limit as h approaches 0 of f of, well, in this case, I should bet not x plus h, but t plus h minus f of t over h, right? Well, I'm told that I know that my time is at 4 seconds. So I can put a 4 here, and I can put a 4 here, right? So I want to find the f at, my bad. I want to find the limit h approaches 0 of f at 4 plus h minus f at 4 over h. All right? Now, doing a little bit of algebra, let's see, f at 4 plus h, well, that f of x, or f of t was 5t squared, so that should be 5 times 4 plus h squared minus 5 times 4 squared, right, over h. Again, but don't forget that I said f of t equals 5t squared, right? Remember that if I have f at 4 plus h, that tells me to replace t's with 4 plus h. Agreed? Okay? So hopefully this limit makes sense now, right? And now I just simplify the numerator, right? If I did that, I get 5 times 16 plus 8h plus h squared minus 5 times 16 is 80 all over h. Right? Distributing the 5, I get 80 plus 40h plus 5h squared minus 80 all over h. Again, I can't evaluate this limit as long as I've got this h in the bottom. But watch what happens. Don't the 80s cancel? I'm left with the expression 40h plus 5h squared over h. Well, I can factor out an h in the numerator and come up with h parentheses 40 plus 5h over h. The h's cancel now, and by doing that, I can now evaluate this limit as h approaches 0. Plugging the 0 in for this h, I would get the answer to this limit would just be 40 plus 5 times 0, which is 40. So what I've just found is the instantaneous rate of change at t equals 4 would be approximately 40 meters per second. And I use this idea of what we're going to later call this the difference quotient to figure that out. Guys, I hope that was short and sweet. Talk to you later.